welcome to the deep dive. Today we're setting off on, well, a truly epic story. The history of artificial intelligence.
It really is.
Our guide for this journey is a pretty comprehensive historical overview from Wikipedia. It takes us all the way from ancient myths to, wow, the very latest AI stuff in 2025.
Yeah, and what's fascinating right from the start is how long humans have actually been captivated by this whole idea of creating intelligence, centuries before we even had the first computers.
Right.
So this isn't just a story about code, it's really about a kind of long-held dream, you know?
Exactly. And our goal for you, the learner, is to sort of navigate this huge history. We want to pull out the key developments, those surprising turns, and the real aha moments, without getting too bogged down in like overly technical details.
Let's make it clear.
Yeah. Okay, let's unpack this, starting way, way back, before computers even existed.
Right. The human fascination with artificial beings, it really stretches back to antiquity. Think about the Greek myth of Talos.
Oh yeah, the bronze giant.
That's the one. The guardian of Crete you read about in stories like Pseudo-Apollodorus' Bibliothèque and the Argonautica. He was this imagined artificial being, you know, powered by some mysterious force.
Wow.
It really speaks to this ancient desire, this urge to create life, or at least something like it.
Like a very early kind of imagining of a powerful self-operating machine, isn't it?
Totally.
And this theme, it just keeps going through the medieval period with all sorts of legends.
Oh, definitely.
You've got Paracelsus, the alchemist, claiming he could create an artificial man.
Right.
Jewish folklore gives us the golem.
Animated by sacred writing, yeah.
And Islamic alchemists exploring Takwin, the artificial creation of life. Even Goethe in Faust features the homunculus.
Right. These stories, I mean, they're fantastical, obviously, but they show this persistent human curiosity about what it actually means to be alive, to be intelligent.
Yeah, it's more than just entertainment.
Exactly. They reveal this fundamental curiosity about the nature of life and intelligence itself. And if you connect this to the bigger picture, these early imaginings, however, you know, far-fetched they seem now, they kind of laid a conceptual foundation for future scientific inquiry. They kept the question alive, could we actually create something like ourselves?
And then we kind of shift, don't we, from pure imagination to actual attempts at creation with automata.
Yes, these incredibly intricate, realistic, humanoid figures.
Built by inventors throughout history?
Yeah, we're talking Yan Shi in ancient China, hero of Alexandria, Al-Jazari during the Islamic Golden Age, leading right up to Jacques de Vaucanson's famous mechanical duck.
The duck. Always the duck.
And Leonardo Torres y Quevedo's really ingenious automated creations.
These weren't just like fancy toys, though, were they?
Not at all. They were demonstrations of incredible skill and a continuous effort to mimic living beings mechanically.
What's significant about the automata, then? Is it that shift?
Yeah, I think it's the transition from pure thought to tangible creation. These weren't just stories anymore. They were physical attempts, however basic, to replicate human form and function. And if you think about it, they hinted at the possibility maybe of intelligence arising from mechanical processes. We also have legends like Roger Bacon's brazen head or the Norse myth of Mimir's talking head.
Right, suggesting artificial wisdom.
Exactly. Not just artificial movement, but maybe artificial thought.
Okay, so from mythical beings to these mechanical marvels, the idea of artificial intelligence was sort of slowly taking shape in the human imagination.
Definitely.
But to move beyond just, you know, imitation, we needed something more fundamental.
Formal reasoning.
Exactly. This is where the early philosophers come in.
Yeah. The development of structured deduction. Thinkers in China, India, Greece.
Aristotle.
Aristotle, definitely. His work on logic, Euclid's systematic approach to geometry. These provided the very basis for formal thought.
And algorithmy.
Crucial. He didn't just give us algebra, but also the concept of an algorithm.
A step-by-step procedure.
Right. A step-by-step procedure for solving a problem. This whole idea of breaking down reasoning into logical steps, absolutely key for AI.
And then much later, in the 13th century, Ramon Llull created his logical machines.
Yeah. Designed to generate knowledge almost automatically. It's a fascinating, really early vision of computational thinking.
Almost automating thought itself.
Llull's work is, well, it's truly remarkable for its time. This idea of mechanizing the process of generating knowledge, It directly influenced thinkers like Gottfried Wilhelm Leibniz,
Okay.
who, along with Hobbes and Descartes, explored this possibility of reducing rational thought down to calculation.
Like math could solve everything.
Leibniz even dreamed of a characteristica universalis, a universal language where basically all disagreements could be resolved just by doing the math.
Wow, imagine that, like settling arguments with a calculator.
Kind of. It sounds almost like science fiction from centuries ago, doesn't it?
Totally. And this idea, reducing thought to calculation, becomes absolutely central as we move towards mathematical logic.
Mm-hmm.
We see these major breakthroughs. George Boole's laws of thought,
Friedrich's Begriffsschrift.
and then the massive one, Principia Mathematica, by Russell and Whitehead.
Yeah, this is all about formalizing the very foundations of mathematics using symbolic logic, putting it all on a really solid logical footing.
And what's fascinating here is David Hilbert's challenge,
Yeah.
right? Could all of math be formalized?
Exactly. And the answer, well, it was surprising. It came from Gödel, Alan Turing, and Alonzo Church. While their work showed there were inherent limits to what logic could achieve.
Gödel's incompleteness theorems.
Right. But it also showed that within those limits, any form of mathematical reasoning could, in principle, be broken down into a series of computational steps.
Okay.
Turing's theoretical machine, just a simple device manipulating symbols, and the Church-Turing thesis,
Which says,
basically that any computable function can be computed by a Turing machine. This was pivotal. It implied that mathematical reasoning itself could be mechanized. A profound insight.
absolutely profound. So the idea of mechanized reasoning is one thing, but you actually need the machines to do the calculations.
Right.
Which brings us to the history of computer science.
Yeah, the calculating machines. Leibniz had ideas. Jacquard with his programmable looms.
Punch cards.
Exactly. And Charles Babbage and Ada Lovelace with their incredibly ambitious analytical engine.
And Lovelace even speculated about it, thinking, didn't she?
She did. She saw potential beyond just calculations, truly ahead of her time.
Then World War II comes along.
Massive accelerator. It led to the development of the first modern electronic computers. Konrad Zus's Z3 in Germany. Turing's Colossus, crucial for code breaking at Bletchley Park. The Atanasoff-Berry computer in the U.S. And then ENIAC.
ENIAC, the big one.
Yeah, the electronic numerical integrator and computer, built on the theoretical work of Turing and John von Neumann, hugely influential. So by the mid-20th century, all the pieces were kind of falling into place. You had the long-standing dream of artificial beings, you had the development of formal reasoning, and you had the creation of physical machines capable of complex computation. They'd all converged.
Okay, so this is where it gets really interesting. All the groundwork is laid. Now we arrive at what's called the official birth of artificial intelligence. Roughly 1941 to 1956. What were the key intellectual sparks that actually ignited this new field?
It was really a powerful combination of several groundbreaking ideas all coming together at roughly the same time. Neurology was starting to understand the brain as this interconnected electrical network.
Okay.
Norbert Wiener's field of cybernetics was exploring ideas about control and stability in these networks, both biological and artificial. Claude Shannon's information theory gave a mathematical framework for understanding digital signals.
Right.
And of course, Turing's theory of computation showed the fundamental power of digital computation itself. The overlap, the synergy between these fields, it strongly suggested this exciting possibility. Maybe we could build an electronic brain.
Wow. It must have felt like a moment of just incredible potential. All of these different lines of inquiry suddenly connecting.
Absolutely.
And figures like Alan Turing were right there actively exploring this exact notion of machine intelligence.
Turing's contribution here is just immense. His 1950 paper, Computing Machinery and Intelligence.
The famous one?
Yeah. He directly tackled that really challenging question. What does it mean for a machine to think? And he proposed his now famous Turing test.
Right. Can a machine fool a human into thinking it's human?
Pretty much. The core idea, if a machine could hold a conversation that's indistinguishable from a human's, then, well, it's reasonable to say it's thinking. It was revolutionary. Its brilliance wasn't really in definitively answering what intelligence is, but in shifting the focus.
To behavior.
Exactly, to a measurable behavioral standard. A really pragmatic move that bypassed centuries of philosophical debate.
I was seriously clever.
Yeah.
Sidestepping a huge philosophical knot.
Yeah.
Around the same time, we also saw big developments in neuroscience, right? Donald Hebb.
Yes, Hebb's work on how learning happens in the brain. The idea that Cells that fire together wire together.
Classic phrase.
It is. And this concept of associative learning, it was hugely influential for AI.
And also,
Well, Hebb's theory provided a biologically plausible mechanism for how learning could occur in artificial systems. This directly inspired early research into artificial neural networks.
okay.
Back in 1943, Warren McCulloch and Walter Pitts created this simplified mathematical model of artificial neurons. They showed how interconnected networks of these things could perform basic logical operations. They essentially laid the groundwork for what we now call neural nets.
Wow, 1943.
Yeah, and one of their students, a young Marvin Minsky, along with Dean Edmonds, built the first actual neural network machine, called CENARC, in 1951.
CENARC. So we have the theory and the very first physical implementations of these networks. What about actual robots? Things they could move around.
The 50s also saw the emergence of these early experimental robots, William Grey-Walter's tortoises,
The turtles.
and the Johns Hopkins beast. What's remarkable about them is they weren't controlled by digital computers like we think of robots today.
No. How then?
They used entirely analog circuitry.
Analog. Wow.
Yeah, to exhibit really rudimentary forms of autonomous behavior, like seeking light or avoiding obstacles. Simple stuff, but analog.
It's amazing to think of these purely analog things as ancestors of today's digital robots. What role did games play in these early explorations?
Games were perfect. An ideal controlled environment to test out early AI ideas.
Like chess and checkers.
Exactly. In 1951, programs were written to play checkers and chess. Christopher Strachey did checkers, Dietrich Prince did chess. Arthur Samuel's checkers program, though, was particularly significant.
Why that one?
Because it incorporated early machine learning techniques. It could actually improve its play over time by learning from its experiences.
Learning.
Yeah. Game AI quickly became this recurring benchmark for measuring progress in the field. It let researchers clearly define goals and measure a machine's ability to think strategically within those rules.
Like a clear proving ground, you can see if it's getting better.
Precisely.
Now, alongside these neural network and cybernetic approaches, we also see the rise of symbolic reasoning.
Yeah.
That became dominant, right?
Yes, for a long time, this was a very, very influential approach. The core idea was that manipulating abstract symbols.
Not mimicking the brain's structure.
Exactly. Manipulating symbols, like logic or language, could be the fundamental basis of thought. In 1955, Alan Newell and Herbert Simon developed the logic theorist program.
What did it do?
It could actually prove theorems from Russell and Whitehead's Principia Mathematica. It even found more elegant proofs than the originals in some cases.
Wow.
Simon famously made this really bold claim that they had essentially solved the venerable mind-body problem.
Oh, so?
By showing that a physical system, a computer program, could exhibit intelligent behavior, manipulate symbols meaningfully. This symbolic reasoning approach, focusing on high-level symbols, it would heavily shape AI research for decades.
That's a pretty audacious claim. Solve the mind-body problem.
Oh.
Okay, so with all these different threads converging, neural nets, cybernetics, game AI, symbolic reasoning, we arrive at a truly pivotal event, the Dartmouth Workshop. Summer of 1956. Widely considered the formal birth of AI as an academic discipline. What exactly happened there?
The Dartmouth Workshop, yeah. Organized by Marvin Minsky and John McCarthy, Claude Shannon and Nathan Rochester were key players too. It was truly foundational. The proposal for the workshop itself stated the intention to explore whether every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it.
That's quite a mission statement.
It really is.
Yeah.
And it was at this landmark workshop that John McCarthy officially coined the term artificial intelligence.
I'll give a name.
Gave it the name. Key early researchers like Ray Solomanoff, Oliver Selfridge, Newell, Simon, they were all there. Newell and Simon even presented their logic theorist program.
Showing it off.
Yeah. This event gave AI its name, its initial mission, its first big, tangible success story, and it brought together many of its pioneering figures. It really launched the field.
So Dartmouth was the official launch party for AI, basically.
You could say that.
And it coincided with something called the cognitive revolution. What was that about, and how did it connect to AI?
Right. The autumn of 1956 marked this fascinating convergence of ideas across seemingly separate fields. At a big meeting at MIT around the same time as Dartmouth, Newell and Simon presented their logic theorist work again. Noam Chomsky discussed his revolutionary ideas on generative grammar in linguistics.
Dowski, yeah.
And George Miller presented his influential research on short-term memory limits, the magical number 7, plus or minus 2.
Famous paper.
Very famous. Miller himself realized that these areas, psychology, linguistics, and this new field of computer simulation, they were all exploring different sides of the same fundamental question. How does the mind work?
Ah.
This realization sparked the cognitive revolution, an interdisciplinary shift. It led to the development of symbolic AI, generative linguistics, cognitive science, cognitive psychology, cognitive neuroscience, and philosophical schools like computationalism and functionalism.
Yeah, a lot came out of that.
Yeah. The common thread was this focus on understanding mental objects, thoughts, memories, knowledge using high-level symbolic representations, which was a significant departure from the earlier behaviorist approaches in psychology, which focused only on observable behavior.
It sounds like a really exciting, optimistic time. Different fields all coming together to explore intelligence.
Yeah.
So what followed this initial burst, the period of early successes, 1956 to 1974?
Yes, the years right after Dartmouth were characterized by, well, pretty impressive progress, at least in terms of what computers were starting to do. Programs were developed that could solve algebra word problems,
Yeah.
prove geometric theorems, even learn to understand and use natural language like English. For many people, this was truly groundbreaking, seeing machines do things that seemed uniquely human.
I can only imagine the buzz, the sense of possibility. And fueled by these early wins, there must have been huge optimism in the research community.
Oh, absolutely. Researchers were incredibly optimistic. You see it in their discussions, their papers. Bold predictions about fully intelligent machines arriving soon, often within 20 years, were quite common.
Really? 20 years?
Yeah. Prominent figures like Simon and Newell, Minsky too, made these really confident predictions. And this strong sense of potential, naturally, it attracted significant funding, especially from government agencies like DARPA.
DARPA, the Defense Advanced Research Projects Agency.
That's them. They poured money into AI research.
So the financial support was definitely there, and dedicated AI research centers started popping up at universities.
Exactly. Dedicated AI labs were set up at top places: MIT, Carnegie Mellon, CMU, Stanford, University of Edinburgh over in the UK. These became the main hubs for AI research, attracting talent, grabbing funding, and really shaping the direction of the field for years.
Got it. And what were the main approaches, the main methodologies being explored during this early success phase?
Several key approaches really dominated the landscape then. One major area was thinking about reasoning, planning, and problem solving as a kind of search.
Search.
Yeah, represent problems as a space of possible states, then develop algorithms to systematically explore these states to find a solution. Heuristics, rules of thumb, were crucial for guiding this search and managing the huge number of possibilities, the combinatorial explosion.
Right, things get complex fast.
Very fast. The general problem solver, the geometry theorem prover, SAINT for algebra problems, strips for robot planning, these were all examples of this search-based approach.
So, like navigating a massive maze, using clever shortcuts to find the way out.
Pretty much.
What about natural language? That still feels like a huge challenge today. What were they doing then?
Natural language processing, yeah, it was another major focus right from the early days. Programs like Student could solve algebra word problems written in English.
Right.
Semantic nets were developed as a way to represent knowledge, organizing concepts and their relationships in a network structure. Early work by Ross Quillian, later stuff like Roger Schenk's conceptual dependency theory.
Okay.
And then there was Eliza, Joseph Weizenbaum's famous chatbot.
Ah, Eliza, the original AI therapist.
Kind of. Eliza could carry on surprisingly coherent conversations just using simple pattern matching and rephrasing tricks. It fooled some users into thinking they were talking to a real human therapist.
Incredible. It's fascinating to see the roots of today's chatbots way back then. Another approach you mentioned, microworlds. What was the idea there?
The idea behind microworlds, particularly pushed by Minsky and Seymour paper at MIT, was to simplify the challenge. Focus research on artificially constrained, well-defined environments.
Like a mini world.
Exactly. The blocks world, just colored blocks on a flat surface, became a really popular testbed. Researchers like Gerald Sussman, Adolfo Guzman, David Waltz, Patrick Winston, they made big contributions in machine vision and language understanding within this limited world. Terry Winograd's SHRDLU was a particularly impressive program. It could understand and act on commands in the blocks world using ordinary English. The goal was basically make progress on core AI problems, but in a setting you could actually manage.
It's like tackling a smaller, controlled version of the big problem to figure out the fundamental principles first.
Precisely.
And finally, we had those early explorations of neural networks with perceptrons.
Yes. While symbolic AI got most of the attention and funding then, research into neural nets did continue. Frank Rosenblatt introduced the perceptron in 1958. He was super optimistic about its potential to learn, even do things like language translation.
High hopes.
Very high. Bernard Widrow and Marcian Hoff developed Adeline and Madeline. Jack Rosen and James Anderson built the Minos machines. But this initial enthusiasm got significantly dampened by Marvin Minsky and Seymour Papert's influential 1969 book, Perceptrons.
What did it say?
It rigorously analyzed the limitations of single-layer perceptrons. It highlighted what they could do, but more importantly, what they couldn't do, like solving the XOR problem.
Okay.
Its publication led to a big decline in funding for neural network research. For roughly a decade, the competition for limited research funds basically meant the symbolic AI approach stayed dominant.
Wow. So that book really put the brakes on connectionism for a while. A setback compared to the apparent successes of symbolic AI.
Definitely felt like it at the time.
And the funding for all this research, it was largely DARPA, right?
Yeah.
But with a relatively hands-off approach initially.
Exactly. DARPA gave substantial grants to the major AI labs. Their philosophy then was more about supporting talented people rather than dictating specific projects, which fostered a really creative, exploratory atmosphere. But as we're about to see, that approach wouldn't last forever.
No, it wouldn't. Because all that initial optimism, all those predictions, they eventually ran into some pretty significant roadblocks, didn't they?
They did.
Leading to the first AI winter, roughly 1974 to 1980. What were the main reasons for this downturn?
The first AI winter was triggered by, well, a bunch of factors coming together. Researchers had seriously underestimated the sheer complexity of achieving general human-level intelligence.
Right.
Those early successes, while impressive demos, often worked only in very narrow artificial domains. Scaling them up to complex, real-world problems proved incredibly challenging.
And the hype.
The massive optimism of the 60s had also created unrealistically high public expectations. When AI failed to deliver on those grand promises in the expected time frame, funding agencies started losing faith. They cut back support. The fundamental techniques they were using just weren't powerful enough for real-world intelligence.
So the limits of the tech and the approaches became painfully clear. What were some of the specific technical problems they were hitting?
Several key problems really emerged as major obstacles. Limited computer power was a big one. Memory, processing speed, just not enough for truly complex AI tasks back then. The issue of intractability and that combinatorial explosion also became a huge concern. Many problems AI was trying to solve were later shown by people like Richard Karp to be computationally very hard. Exponential time problems.
Meaning the resources needed just ballooned.
Exactly. Grew exponentially with the size of the problem. Quickly overwhelmed even the best computers of the day.
Sounds like hitting a fundamental wall.
Pretty much. Then there was what we now call Moravec's paradox.
What's that?
It's the counterintuitive finding that tasks that seem easy for humans, basic perception like seeing or hearing, simple motor skills like walking or grasping, turned out to be incredibly difficult for AI.
But hard stuff was easier.
While tasks humans find hard, complex math, playing chess were relatively easier for AI programs.
Weird.
It is. This paradox highlighted that the symbolic reasoning approaches dominating early AI weren't well suited for the kind of intuitive, unconscious skills that underpin everyday human intelligence.
Right. And common sense.
The sheer volume and diversity of common sense knowledge proved to be a massive, largely unaddressed hurdle. AI programs needed vast amounts of implicit knowledge about the world just to function effectively in real situations. And trying to represent this knowledge and the nuances of common sense reasoning using formal logic ran into all sorts of problems: frame problem, ramification problem, qualification problem. Endless exceptions and qualifications needed.
It's like trying to write down everything we just know about the world.
Yeah.
Impossible.
Practically, yeah.
And all these challenges naturally led to funding cuts. How did that actually play out?
Funding agencies, both in the US and the UK, got increasingly critical. They weren't seeing the big progress they had been promised. The ALPAT report in '66, for instance, hammered machine translation research, led to big funding cuts there.
Okay.
Then in '73, the influential Lighthill report in the UK gave this highly critical assessment of AI's overall achievements versus its goals. That resulted in the near dismantling of AI research efforts in Britain for a while. In the US, DARPA also significantly cut back funding, especially for speech understanding research at CMU. Plus, the Mansfield Amendment in Congress shifted DARPA's focus toward more mission-oriented, directly applicable research, less basic, exploratory science.
So a definite shift away from fundamental AI towards immediate practical applications.
Yes.
But despite these setbacks and this whole narrative of an AI winter, was all AI research completely frozen? Did everything just stop?
That's a really crucial point. While funding at some of the big visible AI labs definitely decreased, the term AI winter can be a bit misleading if you think it means a complete standstill. Historian Thomas High, for example, argues public interest in AI actually kept growing. The number of AI researchers might have even increased slightly.
Really?
Yeah, and new ideas in areas like logic programming, ways to represent common sense knowledge. They were actively being explored. Nielsen, a top AI researcher, even described this period as exciting to be in AI, with new approaches being investigated.
Huh. So more of a reevaluation and a shift, not a total freeze.
Exactly, a reassessment and exploration of new theoretical frameworks, even if the big money wasn't pouring in like before.
Interesting. And this period also saw some major philosophical and ethical critiques aimed at the very foundations and goals of AI, right?
Yes, several influential philosophers raised fundamental objections. John Lucas famously used Gödel's incompleteness theorem to argue that computers, as formal systems, could never replicate the full scope of human understanding and creativity.
Okay.
Hubert Dreyfus offered a really strong critique of symbolic AI's assumptions. He emphasized the crucial role of embodied experience, unconscious know-how in human intelligence. He argued AI's focus on manipulating abstract symbols could never capture this essential aspect.
The physical body matters.
Right, and John Searle's widely debated Chinese room argument challenged the idea that a computer program, just by manipulating symbols according to rules, could genuinely understand anything or have real intentionality.
An understanding question.
Exactly.
These are powerful arguments, really getting at the core of thinking and understanding and whether machines can truly do it. How did AI researchers react?
Initially, many tended to just dismiss these philosophical arguments. They saw the immediate technical challenges as the main thing to worry about.
Focus on the engineering?
Yeah, there was often this sense that once the engineering hurdles were cleared, these philosophical objections would just sort of dissolve. Marvin Minsky famously said of Dreyfus and Searle that they misunderstand and should be ignored.
Approach.
Yeah, but the ethical implications also started surfacing more. Joseph Weizenbaum, the guy who created ELIZA,
Right.
he became increasingly concerned about AI misuse, especially in sensitive areas like psychotherapy, where users might be misled into thinking they were interacting with a genuinely empathetic human.
So, alongside the technical and funding issues, there were these growing questions about the fundamental nature and ethical responsibilities of AI.
Definitely.
But even amid this so-called winter, you mentioned progress continued in certain areas, particularly logic.
Absolutely. Logic had been foundational since the early days, championed by people like John McCarthy. During this period, significant advances continued in logical approaches. J. Allen Robinson developed the resolution and unification algorithm, a powerful general method for automated theorem proving.
Okay.
In Europe, Robert Kowalski and researchers in France developed Prolog, a successful logic programming language using a computationally tractable subset of first-order logic.
Prolog, right.
Yeah. The principles of logic programming and rule-based systems became really influential in developing expert systems later on. And they also continued to inform work on unified theories of cognition by Newell and Simon.
But this focus on logic wasn't universally loved, was it?
No, it faced critics who argued that human problem-solving often doesn't rely on strict, formal, logical deduction. Humans are messier.
So a fundamental difference. The neat logic approach versus the scruffy reality of human thinking.
Pretty much.
And this divide showed up in the different research cultures at places like MIT versus Stanford or CMU.
Exactly. Stanford, CMU, Edinburgh became strongholds of the more logic-based, neat approach. MIT fostered a somewhat contrasting culture, often called the scruffy approach. particularly associated with Minsky, Papert, Roger Schenck.
Scruffy's versus needs.
Basically, yeah. These researchers focused on problems that seem to need more human-like thinking. Understanding stories, recognizing objects in complex scenes, using common sense. They often use less formal, more intuitive methods. Minsky's frames for representing stereotypes.
Right.
Schenk's scripts for understanding event sequences. Key examples of the Scruffy approach.
Okay.
This difference in methodology led to ongoing debates with the logic folks, but it also spurred the development of non-monotonic logics, ways to handle default reasoning and exceptions better than traditional logic could.
So even during the winter, different schools of thought were active, exploring new ideas, pushing boundaries in their own ways.
Absolutely. It wasn't dead, just diversifying, maybe.
And this groundwork eventually paved the way for a resurgence, didn't it? The boom period, 1980 to 1987, driven largely by the rise and widespread adoption of expert systems.
Yes.
What exactly were expert systems and why did they suddenly take off?
Expert systems were AI programs designed to solve problems or give advice, but within very specific, well-defined areas of knowledge.
Narrow domains.
Very narrow. They typically used a set of logical rules, usually derived from human experts in that domain, to reason about the information they were given. Early influential examples were Dendrol helped chemists figure out molecular structures, and MYCIN gave diagnoses and treatment advice for infectious blood diseases.
So why did they succeed where earlier AI hadn't commercially?
The key reason was they offered tangible, practical value. They solved real-world problems, something previous AI hadn't consistently delivered. By focusing on narrow domains, they avoided that huge challenge of general common-sense reasoning, and their rule structure made them relatively easier to develop and maintain, at least compared to more complex AI approaches at the time.
So finally, AI was delivering practical solutions businesses could actually use.
Exactly. Payback time, in a sense.
And this led to a huge surge in investment, both corporate and government.
Precisely. The success of early expert systems like R1 at Digital Equipment Corporation, used for configuring computer systems, reportedly saved them millions.
Wow.
That led to widespread interest and adoption by corporations everywhere. A whole support industry popped up. Companies like Symbolics, Lisp Machines, IntelliCorp, Aon, specializing in AI hardware and software.
The ecosystem grew.
Yeah. And governments jumped back in, too.
Wow.
Japan launched its ambitious fifth-generation project.
What were they aiming for?
Major breakthroughs in conversation, translation, image interpretation, advanced reasoning, using Prolog as a key technology.
Big goals.
Huge goals.
Yeah.
Other countries responded: the UK's ALVI project, the US's Microelectronics and Computer Technology Corporation, MCC, and DARPA's Strategic Computing Initiative. Big funding programs. The whole AI industry just boomed. From a few $1 million in 1980 to billions by 1988.
Billions. That's incredible growth. Sounds like a real golden age for AI, fueled by these practical, knowledge-driven systems.
It certainly felt like it.
And this boom also brought a new focus on the importance of knowledge itself, right?
Absolutely. The success of expert systems really underscored the central role that domain-specific knowledge plays in intelligent behavior. This led to what was often called the knowledge revolution. More emphasis on knowledge-based systems, knowledge engineering.
Building the knowledge base.
Right. Researchers realized that sophisticated reasoning often relies on having access to and being able to use large amounts of diverse knowledge. Ambitious projects like Douglas Lennett's Psych tried to tackle the common sense problem head-on by trying to build this massive, comprehensive database of everyday facts and relationships, encoding common sense.
The idea being that maybe the secret to intelligence isn't just the algorithms, but also having this vast library of world knowledge.
That was definitely a key idea driving things then.
But this period of rapid growth and huge optimism, it didn't last forever either, did it?
No, it didn't.
The late 80s, early 90s saw the start of a second AI winter. What caused this downturn?
The second AI winter was, in many ways, a consequence of those overinflated expectations that had built up around expert systems during the boom.
The hype cycle again?
Exactly. While these systems were useful in specific narrow domains, they also showed significant limitations. They were often very expensive and difficult to maintain, update. They couldn't really learn from new information or adapt easily, and they tended to be brittle.
Brittle, meaning?
Meaning they could fail unexpectedly or give nonsensical results if they encountered inputs outside their very limited area of expertise.
Okay, not very robust.
Not really. Also, the market for specialized AI hardware, those Lisp machines designed for AI programs, it collapsed.
Why?
Because general-purpose desktop computers just got more powerful and much cheaper, good enough for many AI tasks.
Right, economics.
Yeah, and government funding started getting cut back again. DARPA's Strategic Computing Initiative, for example. The promised breakthroughs weren't quite materializing on schedule. Japan's ambitious fifth-generation project, while it generated a lot of research, ultimately didn't hit its really optimistic goals by 1991.
So missed targets, brittle tech, cheaper alternative.
Put it all together,
Right.
and the business community lost confidence again. Resulted in shutdowns, bankruptcies, acquisitions. Over 300 AI companies went under or got bought out by 1993.
Wow, another cycle of intense hype, followed by disillusionment and cuts.
Pretty much, yeah.
But it sounds like even during this second winter, AI tech wasn't vanishing entirely, just maybe going undercover.
Exactly. That's a good way to put it. Behind the scenes, AI algorithms and techniques were increasingly finding their way into larger software systems, commercial applications,
Like where?
data mining, robotics and manufacturing, logistics optimization, speech recognition systems, fraud detection in banking, early medical diagnosis support, all sorts of places.
But not called AI.
Often not explicitly labeled as AI, this contributed to what's known as the AI effect.
What's that?
It's the phenomenon where once an AI tech becomes useful and widespread, people stop thinking of it as AI. It just becomes standard technology.
Ah, interesting, like GPS or something.
Kind of. And researchers themselves sometimes deliberately avoided using the term AI in proposals to get funding during that skeptical period.
It's a smart move, maybe.
Pragmatic, certainly. There was also this growing trend towards more mathematical rigor in AI research, more collaboration with other fields like statistics, mathematics, and a focus on tackling specific, well-defined problems with demonstrable, verifiable solutions, what we now often call narrow AI.
A more grounded, less overtly ambitious approach.
Yeah.
Focus on delivering practical solutions to specific problems.
Yes. Building things that demonstrably worked on a smaller scale.
And during this time, the idea of intelligent agents gained a lot of traction as a kind of guiding paradigm for AI research. What are intelligent agents, and why did that perspective become so influential?
The intelligent agent paradigm really got widely accepted in the AI community in the 90s. It draws ideas from decision theory, economics. It defines an intelligent agent as a system that perceives its environment through sensors
Sees the world.
and takes actions through effectors
Does stuff.
to maximize its chances of successfully achieving its goals.
Okay, goal-oriented perception and action.
Exactly. It provided this unifying framework for thinking about AI systems, everything from simple rule-based programs to complex learning systems. It even drew parallels to biological organisms, human behavior. It let researchers break down the huge problem of general intelligence into designing individual agents that could operate effectively in specific environments. The hope was that complex intelligence might emerge from the interaction of multiple agents.
Okay.
And it emphasized rationality, goal-directed behavior in AI.
A more modular, goal-focused way to think about intelligence.
Yeah.
And the late 90s, early 2000s also saw some really high-profile achievements, right? Even if they weren't always branded as pure AI breakthroughs.
Yes, definitely. Despite the AI winter narrative in the business world, significant milestones were being hit. IBM's Deep Blue beating Garry Kasparov at chess in 1997, that was a landmark event, huge public attention.
Even if it was a lot of brute force compute.
Yeah, it relied heavily on massive computation combined with expert chess knowledge programmed in. But still, a machine beat the world champion.
Huge symbolic moment.
Absolutely. And then in the mid-2000s, you had robots from Stanford and CMU doing incredibly well in the DARPA Grand and Urban Challenges for autonomous vehicles.
Self-driving cars starting to happen.
Exactly. But these successes were increasingly attributed not just to clever AI algorithms, but also to big advances in engineering, sensor tech, and just the sheer exponential increase in computing power. Moore's Law.
Right.
Deep Blue's computer, for instance, was vastly faster and more powerful than the machines playing chess back in the early days of AI.
So raw computational power was becoming a really big factor in achieving what looks like intelligent behavior.
Increasingly so, yes.
And this brings us to the more recent period, roughly 2005 to 2017, often characterized by big data, deep learning, and a renewed interest in AGI. This feels like another major turning point.
It absolutely was. The early 21st century saw this convergence of several key trends that led to a dramatic resurgence in AI capabilities and interest. First, the increasing availability of massive amounts of data, big data.
The Internet of Things.
Largely, yeah. Coupled with significantly faster, cheaper computing hardware, particularly the rise of powerful GPUs,
Graphics cards.
graphics processing units, originally for games, but turned out to be perfect for the parallel computations needed in machine learning. This created the perfect conditions for advancing and successfully applying sophisticated machine learning techniques, especially deep learning.
Deep learning, the big one.
Yeah. The breakthrough successes of deep learning around 2012 in image and video processing, natural language understanding, speech recognition, that proved to be a real turning point. Dramatic improvements in performance in these previously really hard areas, and this, in turn, sparked a massive surge in investment in AI research and development from academia, from industry. Everybody jumped back in.
Deep learning seems to have been the key that unlocked a lot of those tough perception and language problems. What made it so much more effective this time compared to the earlier neural network attempts?
The key differences were primarily scale, the sheer scale of data that became available for training these models.
Training data.
Massive amounts, and the dramatic increase in computing power, especially with those GPUs. Deep learning models, with their multiple layers of artificial neurons, they need enormous amounts of labeled data to learn complex patterns effectively. And the computational demands for training these huge models are immense.
Right.
Before the 2010s, these crucial resources, massive data, massive compute, just weren't widely accessible. Plus, earlier approaches, say in image recognition, often relied on manually engineered features.
Like telling the computer what to look for.
Exactly. Human experts decided what aspects of an image were important. Deep learning, on the other hand, lets the system automatically learn the relevant features directly from the raw data.
Much more general.
Much more general, much more powerful. The groundbreaking win of AlexNet, a deep convolutional neural network, in the 2012 ImageNet competition,
Big moment.
decisively demonstrated the power of this approach, triggered a massive shift in the whole field.
A real paradigm shift.
Yeah.
Driven by data, compute power, and these more sophisticated models. And this success also reignited that long-dormant dream, didn't it?
Yeah.
Achieving artificial general intelligence, AGI, true human-level intelligence.
Yes, it did. The rapid progress in what we now often call narrow AI systems, great at specific tasks, led to renewed interest among some researchers in that original, much more ambitious goal of creating AGI. Prominent figures like Ben Goertzel became vocal advocates for more direct research into AGI.
Yeah.
New companies, research institutions, DeepMind, OpenAI were founded with the explicit long-term goal of pursuing AGI.
Aiming for the big prize.
Right. But this renewed enthusiasm also brought back concerns about the potential risks of highly advanced AI. Unintended consequences, even existential threats if superintelligent AI were developed without proper safeguards.
The alignment problem.
Exactly. This led to increased academic research on the alignment problem. How do we ensure the goals and values of advanced AI systems actually align with human values?
So, as the tech capabilities rocketed forward, the ethical considerations and potential long-term impacts became central to the discussion again.
Very much so.
And the sheer amount of data being fed into these models also raised new questions about bias and unintended consequences, didn't it?
Absolutely. As machine learning systems, especially deep learning, got more powerful and deployed in critical real-world applications, disturbing examples of unintended, potentially harmful consequences started popping up.
Like what?
Algorithms that inadvertently contributed to financial instability, evidence of racial bias being encoded and amplified in criminal justice systems, facial recognition tech, often because of biases already present in the training data.
Garbage in, garbage out, amplified.
Essentially. The events around the 2016 U.S. election, the controversy over the COMPAS recidivism prediction algorithm, they further highlighted the potential for misuse and the critical importance of addressing fairness, transparency, accountability in AI systems.
Right.
The value alignment problem, ensuring AI operates according to human values, became a serious growing area of academic study and public concern.
A stark reminder that tech progress isn't automatically good. We need to steer it carefully.
Crucially important.
And this brings us right up to the very recent period, from around 2020 to now, dominated by large language models and another major AI boom. It certainly feels like we're living through a pretty significant moment in AI history right now.
We certainly are. The development of the transformer architecture in 2017 by researchers at Google, that was a crucial breakthrough, especially for natural language processing.
Transformers, what's special about them?
This novel neural network architecture, it has these self-attention mechanisms. They let the model weigh the importance of different parts of the input text. Turned out to be exceptionally good at processing sequential data like text.
Okay.
This architectural innovation paved the way for scaling up and developing massive large language models, LLMs, like OpenAI's GPT-3, DeepMind's Gato. These foundation models trained on just unbelievably vast amounts of unlabeled text data.
The whole internet, basically.
Pretty much. They've demonstrated surprisingly human-like capabilities. Understanding language, generating language, even manipulating it creatively. Impressive abilities in knowledge retrieval, summarizing text, even writing computer code.
And the public release of these LLMs, especially OpenAI's ChatGPT in late 2022, that really blew things up, didn't it? Captured the global imagination.
It was a truly pivotal moment. ChatGPT's remarkable ability to have seemingly natural, coherent conversations, answer all sorts of questions, generate creative content on demand. It led to an unprecedented level of public awareness, fascination, and of course, a massive surge in investment in AI across the board.
Everyone wanted it.
Yeah. Major tech companies like Google, Microsoft rapidly responded, integrating similar LLM tech into their own products, services, Bing Chat, Gemini.
Right.
But this rapid, widespread progress also ignited this intense debate about the societal economic implications. Prominent figures in the field, people like Yoshua Bengio, Elon Musk, Steve Wozniak, even called for temporary pauses on developing the most advanced AI systems.
The pause letter.
Yeah, to allow for better understanding, mitigation of potential risks. At the same time, many others, like Jürgen Schmidhuber, remained highly optimistic about the transformative potential.
A real split. Immense excitement, but also significant unease about the downsides.
Exactly, a very polarized discussion.
And we're also seeing just tremendous financial activity.
Yeah.
Massive venture capital investments, soaring valuations for AI companies.
The investment in AI since 2020 has been truly exponential. VC funding for generative AI startups hit unprecedented levels. The U.S. has been leading in overall funding, startups, AI patents, but the commercial landscape is increasingly dominated by the big American tech companies.
Google, Microsoft, Meta.
Making huge strategic investments, acquisitions. The valuations of companies like OpenAI and NVIDIA making the crucial hardware, the GPUs reached staggering heights. Reflects the immense market demand for AI tech and the underlying compute infrastructure.
It definitely feels like a bit of a gold rush mentality right now.
There's certainly that element.
But there are also voices of caution emerging, right? Concerns about a potential AI bubble, the sustainability of these huge valuations.
Yes, by mid-2024, some prominent financial analysts like Jeremy Grantham, Jeffrey Gundlach started publicly expressing concerns, questioning the sustainability of these high valuations in generative AI, drawing parallels to previous tech bubbles like the dot-com era. They pointed out that many AI companies, despite their tech promise, were still struggling to show clear, profitable, long-term business models.
A crucial reminder, tech innovation doesn't always immediately equal sustainable economic success.
Right, the business model question is still very active.
And even amidst this financial uncertainty, the underlying AI tech itself just keeps advancing at breakneck speed. New LLMs like Anthropic's Claude 3 family.
Absolutely. The Claude 3 models, especially Opus, and then Claude 3.5 Sonnet, they showed significant performance improvements across benchmarks, even beating some of the previous leaders in certain areas. The pace of innovation in LLMs remains remarkably rapid.
And just last year, 2024, we even saw Nobel Prizes awarded that directly recognize huge contributions to the foundations of modern AI in physics and chemistry.
Yeah, that felt like a major recognition of the field's growing impact.
2-1.
The Physics Prize recognized John Hopfield and Geoffrey Hinton for their groundbreaking work on neural networks.
Hinton, yeah, godfather of deep learning.
Right. And the Chemistry Prize honored the development of AlphaFold for protein structure prediction.
DeepMind's protein folding AI.
Exactly. A remarkable achievement powered by deep learning research from Demis Hassabis and John Jumper at DeepMind. This recognition from the highest scientific authorities really underscores the transformative impact AI is having across different sciences.
It really does. And looking at the very latest stuff, right now, January 2025, even more big moves. OpenAI announcing ChatGPT Gov, a version for U.S. government agencies.
Tailored, secure solutions for government.
And the unveiling of this massive infrastructure project, Stargate LLC, backed by OpenAI, SoftBank, Oracle, MGX.
Yeah, that's huge.
with President Trump announcing plans for substantial government investment in it, too.
It really highlights how deeply intertwined AI is becoming with both government and major industries at a fundamental infrastructural level.
It signals a long-term strategic commitment.
Definitely. AI is seen as a core technology that's going to shape the future landscape across so many sectors.
Wow, okay. What an incredible journey we've covered. From ancient myths and, philosophical ponderings to trillion-dollar valuations and Nobel Prizes in just this conversation. To bring our deep dive to a close, what would you say are the most crucial key takeaways from this whole sweeping history of AI?
Well, I think the history of AI is really characterized by these recurring cycles, isn't it? Intense optimism, high expectations, often followed by periods of skepticism, funding cuts, reassessment those AI
Just a
winters.
boom and bust.
Yeah, it's a sortie fueled by fundamental breakthroughs in logic computation, and then the emergence of new paradigms like neural nets and, more recently, deep learning. This current boom, driven by the remarkable capabilities of LLMs, it represents a particularly significant leap forward. It offers immense potential for innovation, transformation across so many aspects of our lives. But crucially, it also raises these profound ethical and societal considerations that we absolutely must grapple with carefully.
And for you, the learner, maybe the most striking aha moment from all this is recognizing that cyclical nature, the winters that follow the booms. It highlights the inherent complexity, the ongoing iterative nature of progress in this field. It's not just a straight lineup.
Not at all.
Or maybe it's just realizing how long this dream of creating artificial intelligence has been around. Foundational ideas stretching back centuries before we even had computers.
Right. Understanding this rich, complex history gives you crucial context for navigating the incredibly rapid advances happening right now. It lets us hopefully learn from past successes and failures, appreciate the long, often winding path of progress, and engage in more informed, more nuanced discussions about AI's potential future impact on our society, our world.
So as we wrap up this deep dive, here's a final provocative thought for you to consider.
Mm.
Given this historical pattern of booms and busts, what might be the next major turning point, or perhaps even the next winter in AI? And what unexpected field of research or seemingly unrelated idea out of left field might just spark the next revolutionary boom that pushes artificial intelligence in entirely new and unforeseen directions? Something to think about. Thanks for joining us for this deep dive.